Good morning, good afternoon, or good evening, depending on where you are at the moment. My name is Pavel Parol. I'm a solutions architect at CodeLime.
And my name is Ignacio Setek. I am software engineer at CodeLime.
Welcome to our webinar. We are very happy you joined us. Please give us some feedback if you can hear us.
You can use YouTube comments, for example, to mention that you can hear us. It would be great for us.
Okay, I hope everything is okay. During our talk, of course, you can answer some questions, because at the end of this webinar, we plan to have some kind of Q&A session. So you can ask of some topics that would be interested for you, or you would like maybe to have more details on some aspects. So we are free, of course, to ask the questions, and we'll try to answer later on. And today we'd like to give you a kind of panoramic view on application networking in Kubernetes. And this is a very, I would say, up-to-date topic with many possible solutions depending on the context and the actual needs the given applications deployed in Kubernetes may have. So our goal for this webinar is first to give you some feeling of what application networking in Kubernetes is. And secondly, what solutions apply to this area and how. So application networking is actually part of a bigger topic, I would say, that is usually just called Kubernetes networking. So we'll start by briefly discussing what it's all about. Then we'll focus on the specificity of application networking based on 5 example use cases. After that, we will complete this picture with a few strictly technical remarks. And finally, we'd like to give you some kind of practical taste. So we plan to present a live demo addressing the problem discussed in one of the use cases.
I think it's worth mentioning that also at the end we will have Q&A session. So if during this talk you will feel like you have some questions, you didn't understand something, or you are curious about anything, just please use the YouTube comments to ask your questions.
Yeah, sure. Okay, so let's start with Kubernetes networking overview. When we talk about Kubernetes networking, I think it's good to know from the very beginning that this is actually a very broad topic. However, there seem to be 3 main points here. The first point is absolutely fundamental, I would say, and is about attachment to network. And here a number of important questions arise, such as how to connect or remove a container to or from a network in the cluster. What should be configured inside a container? So for example, an interface, maybe IP address, a default route, or other routes, or maybe some other parameters like MAC address, MTU, bandwidth, etc. We need to know also what should be configured on the host, and what technologies can be used for that purpose. And this is where the open source CNI project comes in handy. Which provides the so-called CNI specification. And this specification describes how to do all of this in a standardized way. How does it work in practice? So Kubernetes calls the so-called plugins that, based on CNI specification, attach pods to the network in the cluster. And there are many different implementations of plugins that are compliant to this specification. For example, the CNI project itself provides a group of the so-called reference plugins. But frankly speaking, most often in a production-grade cluster, the so-called third-party plugins would be used. Some of them are simple. Some of them are more advanced in terms of the range of functions or mechanism they are based on. So what you need to do is just to choose and then install in your cluster the plugin that just gives you what you really need. or maybe you can have an approach that you just want to use the one that you know that is stable, that's mature enough, reliable, etc. And the second big point is about internal and external communication. So we know so far that pods have been attached to the network and they have IP addresses assigned thanks to the CNI plugins running in the cluster. But now there are other issues that need to be considered. For example, how should pods communicate with each other? Do they need to use IP addresses only, or maybe there is some more efficient approach required? How can pods communicate with the outside world? Maybe there are some specific mechanism offered by Kubernetes to support such scenarios. How about DNS? So Kubernetes comes with the concepts of the so-called services that allow pods to communicate effectively both inside the cluster and with the outside world. And you need to know that services are actually a kind of abstraction only. But there's also a kubeproxy, which is a Kubernetes component that implements the logic behind services. And additionally, Kubernetes offers an internal DNS implementation called Core DNS, thanks to which resources deployed in a cluster can use not only IP addresses, but also domain names to communicate with each other. So those two big points, attachment to network and internal and external communication, are actually some general capabilities that Kubernetes offer in terms of networking, and they define how Kubernetes networking is organized and how it works. If you feel you're not familiar enough with concepts like CNI, CNI plugins, Kubernetes services, kubeproxy, you might want to visit our YouTube channel where you can find some interesting educational content, for example, introduction to CNI or some other videos. So we do encourage to do so. Okay, and the mechanism I mentioned so far are available generally for any kind of user workload that is running in the cluster. But imagine the situation that there's some application that has some specific networking requirements. And then the question is, does Kubernetes offer something to handle such a scenario? So this is where the third big point, which is application networking, arrives. And we'll try to better explain this based on 5 example use cases. The use case number 1 is about providing single entry point for multiple APIs. In the second use case, we consider advanced traffic management. The third use case is about resilience and security. In the use case number 4, we consider fine-grained authorization, and the last use case, the use case number 5, expresses the general need for observability in the cluster. These use cases are pretty general, as you can see, and frankly speaking, we did it intentionally because thanks to such approach, we'll be able to show you that some of them may concern different practical aspects depending on the context, and thus you can propose more than one solution there. Okay, so let's take a look at the first use case. Imagine you have several online stores. Each of them sells completely different things, so they are completely different applications. But they are all running on the same Kubernetes cluster, of course. Now you want your customers to be able to use the same base domain name to access the stores online from the web browser as shown here. Now, how you can do that? First, you need to configure the so-called Kubernetes services, one for each application. And this basically allows you to access the application from within the cluster as well as from the outside. But you need to know that to do this, you use IP addresses and port numbers. And while this may be acceptable to some people, for example, network engineers, for example, it is definitely not for end users, because end users just want simplicity and convenience. They really don't want to remember any IP addresses or any ports. So you do need something more. And here comes Ingress. What is Ingress? Ingress is an API object that manages external access to multiple services in a cluster. It's a kind of proxy, typically for HTTP or HTTPS traffic, so it works on the so-called layer 7. And more specifically, it implements layer 7 routing, which is sometimes called HTTP routing or path-based routing, as you can see in this case. So again, Ingress exposes HTTP routes from outside the cluster to the services in the cluster. And to give you the full picture, the HTTP traffic to be handled by Ingress enters the cluster through cloud load balancer or external proxy server, depending on whether the cluster is deployed in the cloud or you have maybe an on-premise cluster. And finally, a very important point. How is Ingress implemented? Well, Kubernetes doesn't offer any native implementation by itself. Instead, you are free to choose one of the many Ingress controller implementations available on the market, such as Nginx, Ingress controller, Conk, Traffic, Contour, HA proxy. And what is important to know is that they usually are based on some kind of reverse proxy engine inside, such as Envoy, Nginx, or HA proxy. Okay, the second use case is about so-called advanced traffic management. What do I mean by that? First, imagine that you have built a quite complex application following the microservices architecture pattern. And your application has been launched in Kubernetes cluster, and the individual microservices works as pods. Nothing special here. Now suppose your front-end pods are communicating with the API pods within your application architecture. But you have two different versions of the API pods, and you want both to be called by the front-end pods, but you want to be able to decide how many % of traffic coming from the front-end pods goes to each of them. So in other words, you want to distribute such traffic in a completely arbitrary manner. Why do this? Well, today there are many different strategies for deploying and testing applications. For example, canary rollouts, blue-green deployments, or A/B testing. Generally, all of them are based on the assumption that you're able to perform a flexible traffic splitting in your cluster. Now the question is, what do you need to use to be able to distribute traffic between workloads in such a way? Kubernetes doesn't offer any native mechanism for that. It is good to know that, but there is a solution you can onboard to your cluster for that purpose, and this is a service mesh. Service mesh is a kind of additional logic that you add to your cluster to control communication between different workloads running there. So how does it work? An additional container acting as sidecar is injected into each pod. It is a kind of a layer 7 proxy that works in both forward and reverse mode. And such proxies handle calls to and from the microservice on behalf of which they act. So the service mesh is a system that has its own brain, meaning a control plane which configures and coordinates the behavior of such communication and of the proxies. And it must be said that this is a very powerful system, to be honest. because by introducing a proxy to each pod, it gains a very deep insight into the communication between workloads in the cluster. So we can control such flows in a very sophisticated way. Now, going back to our use case, it means that we are able to perform weighted load balancing, for example, and this is exactly what we need there. And just to give you the complete picture, there are not the only functions. I mean, the traffic splitting in a sophisticated way is not the only function that can be offered by the service mesh. There are many more functions. So again, the service mesh itself can be a very, very powerful solution. And there are several service mesh implementations available on the market. Probably the most popular right now is Istio. But there are also Linkerd, Kuma, Nginx Service Mesh, and others. Now let's jump to the third use case. It is a very general, and it expresses the need to provide an appropriate level of network resilience and security for applications deployed in Kubernetes. A very important assumption here is that we do not require it from the application itself, but it must be provided externally, for example, by using some kind of proxy or gateway that will take care of it. And depending on the specific needs, it can perform different functions. For example, a circuit breaker is a kind of mechanism that allows you to block incoming connections to the application when the given conditions are met. For example, the maximum number of concurrent connections has been reached, or a failure threshold for some app has been exceeded. So it works like that. Timeouts and retry settings are other useful mechanisms that prevent the service from being overwhelmed with requests. For example, when there's some failure and the given service is temporarily unavailable. Another feature can be rate limiting. It can help to control the amount of incoming traffic coming to application from outside. And this is a very popular approach for defending against denial of service attacks. And a web application firewall protects applications against other common attacks such as SQL injection, for example. Now the question is, which solution gives you this? Resilience functions are mainly supported by the service mesh implementations, as well as by some Ingress controllers, but as an additional functionality, and this is more or less the same for the rate limiting. As for the web application firewall, there are dedicated implementations that you can use, or again, some Ingress controllers can offer it too. Okay, the next use case. Now let's move to the one with the microservice architecture. So we will go back to this scenario, but now we don't want to talk about traffic splitting, but more about fine-grained authorization. For example, we want front-end pods to be able to talk to the API pods or other application models with which they interact. But we don't want them to talk directly to any database pods, since this is not the best idea in general. This is just an example. And the general idea here is to indicate which workloads in the cluster are allowed to communicate to each other and which are not allowed to do so. To make this possible, Kubernetes provides network policy API object. And thanks to network policies, you can allow or block connections based on IP addresses or ports. So it operates on the layer 3 and layer 4. Now it's important to know that Kubernetes does not provide any default implementation of the network policy logic. So it means that if you create a dry network policy without running the appropriate mechanism in the cluster to execute it, it has no practical effect. So to make this work, you need to do some network plugin that supports network policies. And there are many such implementations, for example, Calico, WaveNet, CubeOVN, Cilium, and more. Additionally, if you need maybe some more granular configurations, you can use the so-called authorization policies offered by the Istio service mesh, and they can work up to layer 7. So then you can also use, for example, HTTP header fields to build your policies for uplink or denying some traffic. And the last use case is about the general need for observability. Sometimes it's maybe hard to define observability, but I guess it can be defined as the general ability to measure a current state of some system or software environment by examining different types of data it generates. And it is based on 3 pillars, which are monitoring, logging, and tracing. So monitoring is a process of continuous gathering of various types of data. Most often they relate to the performance of the system, and therefore they are numerical data in most of the cases, so they are called metrics. Logging, in turn, is the process of registering all kinds of events that happened within an application. And logs can help a lot in troubleshooting, for example. And lastly, tracing is a process that helps to first observe and then analyze the entire life cycle of information flows going across some distributed system. And tracing is most often used in some specific context. What solutions provide these functions? Where there are a lot of them, for example, Prometheus, Pixie, Zipkin, Datadog, Grafana, Hubble, Kiali, Yega, OpenTelemetry. Depending on what you need, you take it and onboard it into your Kubernetes cluster. And generally, you can install them as standalone instances. But some of them may also be delivered as a part of some service mesh implementations, for example. Okay, so these were example use cases that we wanted to show you, to let you understand what application networking in Kubernetes is, to give you some feeling of this, and what aspects it may cover. Now let me give you a couple of a little bit more technical insights of what we just showed. So as you may have noticed when discussing possible solutions for the use cases I presented, I was talking quite a lot, especially about 2, the Ingress and the service mesh solutions. And I think it is very important to be able to correctly identify for which cases mainly Ingress applies and for which a service mesh would be more suitable. Because according to my experience, this may not be clear to everyone. So the Ingress allows you to control the traffic entering the cluster from the outside. And this is sometimes called the north-south traffic. On the other hand, if you need to control east-west traffic, meaning the traffic between services in the cluster, then you will want to use the service mesh, most probably. For example, when you are deploying an application based on microservice architecture, it might be a good idea. And of course, this is a very general distinction. There may also be use cases when you need to use Ingress and service mesh at the same time. It is also good to know that both Ingress and service mesh concepts are subject to ongoing evolution or improvement. Since Ingress is a Kubernetes API object that has been widely used for many years, it has some modifications provided by the vendors, because Ingress itself is quite simple and therefore a little bit limited in terms of the functionalities it can offer. And therefore, Ingress controllers coming from different vendors usually offer a whole range of additional functionality. For example, in the form of custom resource definitions or some annotations. And what is interesting is that they often appear to be quite similar to each other. And therefore, in 2019, some discussions started on the Ingress evolution and proposing a new API of this kind. One of the goals for such an API was to deliver such additional capabilities, but as a part of the core API standard. And another need was to propose a new Ingress configuration model that would assume different users' responsibilities according to the roles they have, for example, like application developer, cluster admin, or infrastructure provider. And all of this resulted in the initiative, which today is called Gateway API, and which is developed by Kubernetes Network Special Interest Group. And when it comes to service mesh implementations, they usually have really powerful capabilities, as we know, but at the same time, they do introduce additional complexity, and they can affect performance, for example, by introducing additional network latency, and by increasing the use of computing resources in general. And this is mainly due to adding a proxy running as a sidecar to each pod. But there are ideas for some optimization in this area as well. For example, the Cilium solution proposes an approach leveraging eBPF technology. And the idea here is to remove sidecar proxies and to replace them with a single proxy for each node in the cluster, just to simplify a bit the overall solution and to optimize resource utilization. Okay, I think it's time for the demo now. So Ignacy, the floor is yours.
Okay. Thank you, Paweł, for this great introduction into the subject. So after we had this theoretical view into our subject, it's time to get a little bit more practice. So we will come back in a moment to our first use case, which Paweł was talking about, when we want the single entry point for multiple APIs. Just to remind you, this use case, we have a Kubernetes cluster with 3 applications deployed on it. One exposes books, 1 games, and 1 videos. Each of them allows users to just download some resources. And in this scenario, before we will improve it slightly, we have these applications that are reachable separately from each other, which is pretty annoying for us. The other problem with this scenario is that users need to access them by their IP address and the port number. This brings a lot of complexity and breaks the user experience, as the standard user is not used to use a regular IP address and especially remember the port for each application. And to make this even worse, each of these applications has different API. So for example, when we want to order a book, we need to specify the endpoint with prefix order, and then we specify the book name. If you would like to take a game, we need to simply specify the game name. We don't provide any prefix here. And if we want to order a video, we need to specify the by prefix. This is really frustrating for us to remember all of these 3 things. So, to simplify this situation, we will bring the Ingress controller to make a single entry point. And now, with this, instead of targeting 3 applications separately, we will have only one target, this Ingress controller. Instead of remembering 3 specific prefixes for our application, we will use only one style, which means that our endpoint is the application name and then the unit name. So for example, when we want to order a book, we specify /books/book name. And if we want to order a video, we provide /videos/video name. It already brings much better user experience. But the biggest advantage of this approach is removing this responsibility from the user to remember the IP address and the port number, but instead use simple domain name. In our example, this will be mystore.mydomain.com. So this name will be, of course, resolved into external IP address, which is provided by the Kubernetes cluster. So there is still IP address, but this is not required to be handled by the user. And as we are talking here about practice, instead of talking simply about Ingress controller, we will use the solution, which is called Contour, which wraps the Envoy solution underneath, which basically is responsible for handling all these functionalities. And because Envoy is the main player here, and because in Codelime we have a strong experience with Envoy, I want to talk a little bit more about this solution. So, as I mentioned, the main logic behind this use Envoy. And all these tools that we can see below, Contour, Emissary Ingress, Glue, or Istio Ingress, are basically wrappers that will use the Envoy functionality and use it in our Kubernetes cluster. So basically, the only thing that we receive here from these 4 solutions is that we don't need to prepare a big configuration so the Envoy works properly with the Kubernetes environment. We simply specify a smaller configuration that will be translated by one of these solutions, Contour in our example, and we'll prepare eventually a normal configuration for Envoy. So to talk a bit more about Envoy, this was originally built by Lyft. It is written in C++, and we can simply access the code because the project is open source. This is actually a great advantage of Envoy because we can not only extend this functionality, but we can even modify the existing functionality if some of our developers notice an issue or just want to make some things differently. There is no problem in forking this repository and handling things our way. And despite the fact that Envoy actually is pretty young solution on the internet, when we compare this to Nginx or HA proxy, it actually already gathered a big community due to its functionalities, due to being open sourced, and a few additional things that this is simply good at it. Okay. So to make it even more interesting, let's take a look at how Envoy actually works. We need to take a look at 3 main concepts that Envoy use. First of them are listeners. Listener is basically a way of telling Envoy where to look specifically for connections. We can specify the address there, and Envoy will take care of listening on this address and then propagating this information further. And where will it propagate? Before sending this to the actual server, to the actual application, it will be propagated through filters. Filters in Envoy are the way of specifying additional operations that we want to make on our traffic. So for example, if we have the HTTP connection, we can tell Envoy to add some specific headers for each HTTP packet before sending this to server to, for example, gather some additional informations, or actually, because this might be required by our server, we can clone the packets that we receive, or we can provide some, for example, role-based access control to make it even more secure. And after Envoy goes with the connection through all these filters, it reaches usually the last filter, which is responsible for propagating the connection to the clusters, which actually define our final targets. In our situation, it will be 3 services from our applications. So book service, game service, and video service. And here we can see the example configuration. At first look, it might look quite big, but just to understand this is the only configuration that we provide, and with this we already gather a lot of functions that otherwise, without using it, we would have to implement into our applications. So a lot of responsibility is taken from us as developers and put into Envoy. To just tell you what's going on in here, at the beginning we have admin section, which allows us to specify additional endpoints which gathers statistics. This is one of great advantages of Envoy, that out of the box we receive a lot of statistics of what's going on with our connections. Below we can see that we have specified in static resources listeners section, and this listener section specify the address where we listen for the traffic, and the filter chain, which is this filter chain that will be used for these connections. And below we have cluster sections, which actually specify where to propagate this connection later and how to propagate it. Okay, so this is a little bigger picture of how Envoy actually works. We can see that we have some actor that sends a request. It is grabbed by the listener, which may decide which pipe and which filter chain should be used here, or should it be dropped. And at the end, we send this to the cluster. So now let's take a look at the demo that we prepared for you. So here we have the environment with the cluster working on locally on our machine. As you can see here, we have a few pod applications, which are for our books applications, our games applications, and our videos applications. And each of these applications provide the service which exposes the port that we can use to reach actually our application. So for example, the books service can be reached with the port 30117. Okay, so just to take a look at how this is going. At first, as we want to access these applications, we need to check what is the node address of our node in Kubernetes. We can say this is 172.1.8.0.2. We will use this address to access our applications. I didn't remember the port name, so I will take one look, 30117. And as this is the books application, if you remember, the prefix here was order, and we specify some book name. For example, I'm a big fan of a book called Blurt, so I will order this one. As you can see, the server responded to us. It said everything is okay. If we would ask for some non-existing book, it would tell us that there is error. And if we would miss our endpoint, we would get an information that this is invalid endpoint. Okay, so this was the bookstore. Let's take a look for the game store. We have here 306613. Okay, and here we have different APIs, so we don't specify any additional prefixes. As you can see, everything is working, and just to make it full, let's take a look at the final application videos. 31573, 311573, and we specify the by prefix, and another great production. Everything is okay. So this is our situation. We need to reach these applications using IP address. We have different APIs. This is bringing us a lot of mess. So to take care of this, the contour exposes us a special Kubernetes object, which is called HTTP proxy. Here we specify that we want to gather applications that will be sent for the host mystore, mydomain.com, and we specify 3 routes that we'll be using here, that we want all connections that will be sent on the books endpoint to be propagated to the books service on their port, and what's much more important, that we want to replace this books endpoint with the correct endpoint, which is in this situation order. Of course, for the games, we will have a different API, as we saw that, and the same goes for the videos. So whenever we create a connection for example, /videos /12 Angry Men, Contour and Envoy underneath will change this endpoint to by 12 Angry Men. Okay, so let's now apply this policy. Everything is working, and now because we are here working locally, we don't have some functionalities just like you would have when you were using the actual cloud, for example AWS, Azure, or I don't know, maybe GCP. You would create a simple DNS provider which would define how to actually resolve this address. So to cheat a little bit, we have written our own script which will basically resolve locally the address from this domain address into external Kubernetes address. So let's take a look. Let's specify the master password, and now we got the information that mystore-domain.com will be resolved to the external IP address, which I believe we can see here, or we cannot see here, so we will quickly leave this place. So now we can finally create a connection to mystore.mydomain.com. And the best part comes now, that instead of specifying these different APIs, we specify /books/blart. Great. I can read my favorite book. I don't need to remember the different APIs. I am very, very happy. Okay, so just to take a look at what's actually going beneath this, we will take a look at the verbose request. So we can see that our domain was actually resolved into our external address. From the request side, there is nothing interesting going on, but from the response side, we can see that the server is Envoy, because this is actually the thing that we were communicating with. Envoy took the responsibility of talking with the server, and we can see that it even set some Envoy specific headers just to work properly beneath this. Just to prove to you that I'm not lying, that this is not only working for books, let's go for the videos. And without the verbose option, we can see that everything here is working properly. We could try at the end, I will quickly tell you, try to access the this address manually, 172.18.0.12 with specifying the port, and we wouldn't get any information here. And the reason for that is this configuration that told that this works only for the host mystore mydomain.com. So if we would override the host header, which we send here, mystore.mydomain.com, it is working. So we have also the possibility of specifying a few other paths here. Okay, so this actually brings us to the end. We are finishing with the demo part here, and we will now head to the questions. So I don't know, let's take a look if we have any questions. Feel free to take your moment and ask them on YouTube.
Okay, so I can see we have already have one. In one use case, observability was discussed, but rather generally. Any more specific examples for application networking? Yes, that's a good point. So our intent was to provide some kind of overview on what observability is. But if you just want some more practical example regarding the application networking, you can imagine a situation that you've got, for example, some application which is deployed in Kubernetes and is based on microservice architecture, for example. So there are different interaction between apps, and imagine that someone from the outside world, some external client, is trying to reach your application. So you can monitor several of important metrics like volume rates, for example, success rates or error rates, things like that. And also you can have some advanced logging. So in terms something is broken, for example, you can log some temporary application downtimes or failures. So you gather all those information together, and then you can make use of some kind of tracing-based analytics in order to analyze why you do have some latencies on some concrete paths in your internal routing between application models. So this is an example use case for that. Okay, any other question?
Hello, Paul. I see that you're introduced. Do you have any questions? Let's just give one or
Gives
two minutes more.
one more chance to ask some questions.
Yeah.
If there are any, we are really happy to answer.
Of course, if you will feel that after this webinar suddenly you will have any question, you can also catch us on the email or perhaps LinkedIn.
Okay, another one. This may not be the context here, but how do we offload any of these policies to something like SmartNIC running on the server running the cluster, expected info on Cilium CNI? Appreciate if you touch. So this is a good question. The Cilium CNI leverage an eBPF technology. So according to my knowledge, eBPF is one of the possibility that can be offloaded to the SmartNIC or general. This can be some kind of the use case for the hardware acceleration. I don't know any details regarding some ongoing works regarding the Cilium. I think the good place to ask would be the Isovalent, which is the vendor of the Cilium CNI. But I believe that maybe they can provide things like that with such kind of functionality. Okay, maybe another question.
Of course, we don't need anymore.
I think we do, because we love to answer questions.
Of course, of course.
Okay. So, like Ignacio said, in case there are other questions, you can just try to reach us via email. So we will try to give you some feedback on that. Okay, so that's basically all that we have prepared for you today. Many thanks for being with us. It was a great opportunity for us as well to be with you and to try to present some topic like application networking, which is a really interesting one, I would say. If you want to contact us on any topic, you can just use the mail that you can see on your screen right now. So once again, many thanks, and see you next time.
Thank you so much. It was a pleasure talking to such great people, and by looking at these questions, we are pretty sure that you were listening to us.
Yeah, yes,
so
indeed.
This is actually a great feeling. Thank you.
Okay, so bye guys, and have a good day.
Bye-bye.